Yeah, thanks for inviting me on. It's a pleasure. My name is Darren O'D, and I've been in I guess, the facade design, building physics industry. It's a small little industry, the building physics industry, here in Melbourne for about 10 years. And yeah, I've had a particular focus on constructability, durability, high performance buildings in general. That's what really my mainstay. And then I guess more recently, I've sort of started a software company too called Speckel. And I also support the members of the Australian Passive House Association. And I'm on the board there in a technical advisory role. So a few little hats there that I wear at different times. So, that's the way it goes. But yeah, all equal love into all of them, I think.
Yep. Yeah. Now there is a few interesting hats there. And you mentioned building physics, probably something that is a little underappreciated historically, because we haven't had to really, worry about it too much compared to internationally. So what are the sort of key fundamentals of building physics that designers need to be paying attention to?
Yeah, look, I mean, when I was at the last large company that I worked for, we looked for a point of difference. We were facade focused, and we said, okay, do we do ESD, which is very, very broad and general, ecological sustainable design? Or do we do something that is more pertinent to the building fabric itself? And you start to think about that and you go, okay, what is that about? It's about air, it's about heat, it's about sound, it's about moisture. So there's this plethora of things that you can look at that directly relate to, the physics of the building and how these elements transfer through a wall system, for example. So really the fundamentals of building physics is that interplay between these different things that are going on and making sure that you kind of tick in all those boxes all at once and making sure you get the best outcome. So that's really a simple way to put it, I guess.
Yeah, and I guess you got those elements of the building, but then also the geographic location, particularly when it comes to moisture. Can you tell us a little bit how the location of the building actually impacts how you think about building physics and, say, envelope design?
Yeah, look, climates, particularly from an Australian context, are highly variable and have a large impact on the durability and resilience of building envelope construction. There's no doubt about it. Relative humidity is a big part of this equation. Its impacts in terms of building envelope construction can be from the outside, in typically warm climates. Let's throw Brisbane in there as a definition. And then it can be from the inside, typically in colder climates. Let's call that Hobart. And then in other climates, such as Canberra or Melbourne, it can be coming from both directions as the relative humidity is seasonally variable. So climates really matter in terms of how we design buildings and where we put particular elements of the building construction, because we want to control relative humidity to a degree, or as much as possible, because its consequences can be quite significant when we transfer that discussion from relative humidity to mold growth or durability or something else.
Can we maybe drill down a little bit on that? So you got relative humidity. I mean, what sort of conditions would lead, or what sort of causal events sort of lead to mold growth?
How does it occur? Like, it's very variable. There's no doubt about it. It's a multi-layered question there. The answer is broad, because you can't really just paint everything with the same brush here, right? So it could be occupant behavior. It could be poor material selection. Could be poor ventilation design, doing things as we've always done them and assuming all sorts of things, or even poor construction. I've perfectly seen all of the above and many other reasons for condensation occurring in buildings. What I can say though is that it is occurring more and more often, particularly in new construction, where we're building tighter and we're insulating our buildings more. And this is not a negative consequence. It's that actually we're needing to design and be a bit smarter about what we're doing if we're going to improve the performance of buildings and ultimately lower the greenhouse gas emissions associated to them. So we shouldn't look at this as this is a negative thing because we're building better. It should be seen as it's a consequence of building better. And we've seen this on other markets. What happens when you build better? You had different challenges. So yeah, it occurs for all sorts of reasons. And yeah, I've seen a lot of them going on out there.
Yeah. So condensation. So how does it actually appear and, generate on a certain layer within, say, a wall build-up? Thinking, relative humidity is one, but also temperature, being another one as well. So how does the condensation occur in that sense?
So how does it occur? Really, air and water vapor is always driving through. Let's use the example of a wall system, and it's kind of looking for the coldest point within that wall system. And typically, this is what we talk about, the dew point. We talk about the point in which the vapor comes through, it meets a cold point, and then it saturates. But it's not the only place that it occurs. You can, if you've got a vapor barrier, so something, let's call that vapor barrier membrane. It doesn't exclusively need to be a membrane. It can be the buildup of relative humidity, and then that turns into water at a point where the actual material can't hold the water vapor anymore. So it must saturate from a physics point of view, and it must drain off somewhere. So there's all sorts of kind of reasons as to why it happens. In reference to timber, timber, we have, identified quite clear boundaries in terms of the amount of moisture content in timber. We want to stay below levels of 16, 18, 20, depends on where you take your reference from, locally or internationally. Depends on what the timber product is made from. If it's heavily processed versus a much more natural timber material, we have moisture content there. So we want to stay below those. And, as soon as we see designs that are theoretically exceeding the 16, 18, 20% mass timber values, then we know that there's a challenge there. So there's multiple ways of seeing condensation and its consequential production of either water as a liquid, or as a result to mold growth, which is the other I guess consequence of high relative humidity. It's either water or mold growth, which is the bits that really start to damage us.
There's a lot that goes into the envelope design. So what are some of the sort of general rules of thumb if we're thinking about timber, whether it's light frame or mass timber, to making sure that we're not going to have any issues?
Yeah, look, there are there's a lot of stuff that goes in there. Those design considerations that I just mentioned there a second ago. It can be materiality, it can be ventilation systems. For me, the ventilation systems are a really important part of it, because there is this over assumption on the market, particularly when it comes to residential buildings. Let's say multi-residential buildings, single facade, facing out to one direction. It's got a sliding door on it. And, we, to a degree, most mechanical services teams assume that door is going to be opened up. It assumes that the extract points in the building, in that particular apartment, let's say the toilets, the laundry, the kitchen, are always going to be turned on. And they've only been designed to meet minimum building code requirements. So there's this massive assumption that vapor gets removed, and the vapor doesn't always get removed. And that's why we have condensation problems in buildings very, very quickly. So yeah, from a ventilation point of view, that there's these over assumptions. And when it comes to the actual construction itself, we want that construction to be vapor open in most cases. We want the construction to be able to handle vapor as it diffuses or as it leaks through that wall, because it will do both. And leakage is far worse than diffusing through a wall. But they're fundamental design considerations that we've got to take into account, particularly when we're talking about mass timber, because mass timber has a natural tendency to allow moisture to diffuse through the system itself. But we've got to make sure that it is a system, not just a throwing in a bit of mass timber and then applying other materials that are unknowns, because they may cause problems in themselves, or when well designed will cause absolutely no problems.
Yeah, absolutely. Well, let's zoom in and consider ourselves a little vapor particle right now, and we're trying to exit the building. I mean, I've always just look at vapor and look at a big solid wall or plasterboard and just think nothing's getting through that. So how does
I know.
Where does it actually get caught up? And like do we have to be thinking about this at every single layer that goes through and consider it from a vapor point of view? I guess, your software solves this problem as well, but how does the vapor sort of get out, and how does it pass through the timber, for example? It's a big solid chunk.
Yeah, look, I agree with Adam. Like I've thought about the same sort of things in the past, like a few years ago. And oh man, surely this wall is just solid vapor is not going to go through there. Well, it will go through there. The diffusion is the easy bit. All materials will allow a level of diffusion, so vapor will diffuse through the system as a function of the pressure difference between inside and outside, and temperature differences between the external and the internal space. And as you stack up those individual materials become a bit of a diffusion party. We've got to understand all of them elementally, and then understand how it will, how each of them will impact the pathway of diffusion through the system. And that's only one part of it. The air leakage is the other part of it. And the air leakage is really the part that only construction can really manage, caulking around your plasterboard, your internal finishes, keeping an eye on any penetrations going through the plasterboard itself, because it will allow air leakage through into the construction layer itself, the structural construction layer. And then that is a major issue. So if we looked at an example, let's say my hometown here in Melbourne, water going through the system, it's primarily going to go through during winter, and particularly at the coldest point of the day, right in the middle of the night. And during winter, it has the highest relative humidity here. So we know the internal is going to be high relative humidity because the external is also high relative humidity at that point in the day. We don't remove relative humidity from our homes, so we know it's going to be there. So in the case of timber, we want to make sure it's vapor open. And we want to make sure that, it has a meaningful way of diffusing through the system that is not allowing for air to leak in there. So, the benefit needs to be sought at the entire system. And then, that's where your original point comes in about the plasterboards and, insulation products and membranes. All of these things need to be open for a system to successfully allow the migration of water vapor through to the outside, where it can drain off on that vapor permeable membrane, and then it disappears from the system, and the job's really done. And I think one of the interesting things about mass timber and CLT as well is that it's inherently airtight as a product anyway, so it allows for the benefits of air tightness, but it also allows for vapor diffusion as well. So, but because of the air tightness, it means that could be a higher level of relative humidity. So it's particularly important to make sure this vapor permeability is well designed for in our different climates.
A key part of the wall build up there you mentioned is the vapor permeable membrane, which I feel like a lot of people are aware of the importance for it. Is there any additional nuance when it comes to vapor permeable membranes that designers need to look out for? Is that, that headline thing, that's all they need to worry about? Or is there actually different levels of vapor permeability within membranes that designers need to be looking for?
Yeah. So look, Adam, I'm sure we're going to get onto the NCC at some point here, but vapor permeability is a part of the equation, right? It is one of maybe 5, maybe 10 different things that probably should be ticked off in terms of what's actually happening within a space. Yes, it's important. Yes, it's important in cold climates, and yes, it's important in building types and spaces that have high vapor loads. But it's not everything. But we'll always want to make sure that we design for natural mitigation of vapor going through the wall to the outside, so we can, mitigate any potential consequences such as mold growth and such as the durability of the actual structure itself. But it's certainly not it's not the most important. There are just things out there that have equal measure. We've got to design for well-ventilated buildings. We've got to design for high performance buildings from a thermal point of view. We've got to protect our structures from a durability point of view. We've got to look at air tightness moving forward, because that has a very positive consequence on the energy efficiency of buildings. So it's a part of it, Adam, but it's kind of not the whole thing. We've got to look at thermal bridges. We've got to look at where vapor is actually being extracted out of the building, whether it just comes straight back in because someone's put it right next to a sliding door. So there's so many things. It's a design philosophy that we've got to get around to, and I think we're getting there. It's just the NCC has only really introduced that now. So it's we're right at the beginning of a fundamental shift to how we deal with this challenge of designing for condensation management, which is that term that gets picked up in the National Construction Code. Segue for you?
Great segue there, Darren. That's good that we coordinate a little bit on the question beforehand. So on that segue, mate, so in the NCC, what sort of DTS provisions are there? What sort of requirements are there? And what sort of modelling do we need to be looking at to actually get past these requirements?
So yeah, look, the National Construction Code has built in a lot of stuff over the years. Condensation management is one of them. It's come in to volume 1 and volume 2. So it's in both commercial and residential now. And it's primarily focused on, where folks are sleeping, and it is driving better discussion in design. It's built on 2 real principles, the DTS and the verification pathway, and both have the performance requirement in the language of the National Construction Code to manage the risk associated with water vapor and condensation. And this is around the need to understand its potential impact on the health of occupants. And really that consequentially then talks about mold growth. It doesn't specifically describe the exact units or anything that needs to be determined. But when it comes to the provision, that DTS versus verification pathway, the DTS solution is primarily focused on that vapor permeability, maybe what you were poking at earlier, Adam. Like vapor permeability is kind of seen as the checkbox, if you like, the way to get things over the line, and it's under pliable building membranes in both volume 1 and volume 2, and it's essentially focused on their application and being located on the exterior side of the insulation layer that form part of the external envelope of a building. So it's there to say, hey, we've got to be designing in colder climates with vapor permeability in mind. So great in respect of that, because it's encouraging us to move away from certain types of vapor barrier, which are pretty much the exact opposite of a vapor permeable membrane. A vapor permeable membrane is permeable, so it allows vapor to transfer through it. A vapor barrier loses its permeability, and it's just a barrier to that diffusion. And that's really important, because it's not something that our industry is fully aware of at the moment, right? It's something that we need to engage on, and certainly architects are learning to specify these things much earlier now. But the more and more we do that, the better we have. And it's probably worth saying as well that even in those groups of vapor permeable membranes, the good ones for cold climates, there's a whole range of products there as well that have different performance values by way of their permeability. So there's some really good products that protect your building, but also consequentially allow the diffusion of vapor through them. So that's what the DTS stuff is about. It's about ticking that vapor permeability box. But of course, we always get a verification pathway in the National Construction Code. It's a performance solution, I guess, in terms of moving forward and trying to meet those performance requirements. And it's really represented by a modeling pathway. And that modeling pathway is there to really emulate your scenario. Let's say you're installing a system into an apartment. You want to be able to take into account the worst case moisture loads from that apartment, and make sure that the moisture is transferred through, and there is a mitigation of any potential mold risk or condensation risk. That's what it's there to do. It's there to just account for that. And there's a fairly elaborate process to go through in order to calculate it. So it's the either tick the box with the DTS, or if you've got something different, a wall type that doesn't quite represent the simplicity of what is defined in the code under that pliable building membrane CTS provision, then you go down this pathway and it allows you far more flexibility. And to be honest, Adam, like we're seeing so many more wall systems out there, so many more roof systems out there that need that pathway, because the simplicity of the NCC just doesn't define so many of our wall systems these days. It's kind of, it's a bit old hat. It's there to represent probably buildings that have been built for the, in the last 50 years, probably not the buildings that are necessarily being built today, because our buildings have got more complicated. So the verification pathway is a good thing for that, from that perspective.
Yeah, absolutely. And helping with another segue, because I'm sure if you can just tell us a little bit about the Speckel platform, why you created it, and I'm assuming it's to help simplify some of these issues that we've been talking about for designers. I mean, I was lucky to have a brief tutorial with yourself last week, and I was blown away by how good the user interface is and how simple it is to actually use, and just get to see the high level of what the results are of different build-ups. So tell us a little bit about Speckel.
Yeah, look, Speckel has been around for a while now. It's almost 3 years old. And I think probably going back to your very first question about the fundamentals of building physics, right? Like we love a loop all the way back to the beginning. Building physics, we're madly into building physics, and we I guess love the ability to apply building physics to improve the outcomes of buildings. And myself and my partner David Carroll, we've come up with a suite of applications that their intent is to, I guess, do a couple of things to specify building envelopes correctly. And when I say correctly, I'm defining correct by whether they fundamentally work from a physics point of view. So whether that's thermal performance, whether it's looking at the life cycle analysis of the system, whether it's looking at condensation. So we want users to be able to jump on there. I shouldn't say users, I should say customers, because the only other people that call their clients users are drug dealers. So our folk on the platform, our clients, they're jumping on there and they're able to very quickly select a system. So we've got some pre-built systems on there. So if they select that system, they kind of know that we've gone through a process and verified the materials within that system. And then they can happily just click and collect, if you like, in the words of COVID these days, that they can be confident that the system has been well thought out, has gone through a process of verification, and can be applied to their project. So it could be just a wall system independently. It could be a roof system just independently, or it could be applied to the whole building to understand its overall thermal performance. And we're going to be looking at some really interesting stuff as we go through this year. And as mentioned just before we kicked off there, Adam, like there's a piece of work that we're about to release that is really exciting in the condensation space. So we have a condensation response on Speckel at the moment, but that condensation response is using, I guess, a standard that is, standards get outdated all the time, and using one of the standards that is now categorically outdated, and we are implementing something that is a hygrothermal simulation, a annual simulation, hour by hour, and you can run it over 10 years if you want to look at the durability of your system over a long period of time. And this is, takes into account all the subject matter that we've just gone through, whether it's a vapor permeable system, how much diffusion, how much leakage there is in that wall system, but it's hand rolled. It's there. So we've done as much as we can in terms of applying logical decision making and just really reducing the amount of inputs required by the user, not because we think the user shouldn't have loads of flexibility. It's just that some of this stuff is really quite detailed and it's condensed into just a very few number of people. So we want to be able to sort of enable people to make these decisions quickly. And if they want to dig down and go through it, then they can. But at the high level, it's there to be applied for anyone. So whether you're a building designer and an architect and someone interested in energy efficiency, a facade engineer, a specifier, like we want as many people to get access to it. And there's a big free component of Speckel, and then there's a paid component, because we've got to get paid at some point for something. So everyone expects everything for free these days, so the free is really free, and it's free forever. And then the really more interesting stuff, the more detailed stuff, is just where the plans come in, and we aim to sort of pick up a few bucks here and there on that, and providing a bit of training and that sort of stuff. So Speckel you can jump on there. It's just Speckel, SPECKEL.io. I'm sure someone can put a reference to that somewhere to this conversation. But that's really it. And happy to chat about it to anyone that wants to listen to me again, but I'm sure you probably won't.